Hello everyone, and welcome to another episode of Math-321. So today we're going to conclude Investigation 27, which is normal subgroups and quotient groups. Okay, so just a few things to remind you of from last time. So let G be a group. A subgroup N of G is normal in G, or is a normal subgroup of G, if AN equals NA for all A in G. So the left and the right cosets are all the same. And then the notation for that is this little triangle thing here. That means that H is a normal subgroup of G. Then we had a theorem that was important that gave us a way to check whether a subgroup was normal. So let G be a group and N a subgroup of G. Then N is normal in G if and only if AN A inverse is a subset of N for all A in G, where AN A inverse is just simply exactly what it sounds like. It's all of the elements A little n A inverse for little n in big N. And then finally we had definition 27.8, let G be a group and N a normal subgroup of G. The quotient group or factor group of G by N is the group G mod N, and this is all of the left cosets where A is an element from G. And of course, since N is a normal subgroup, the left and the right cosets are actually the same. And the operation on this group is the following. To multiply two of these cosets together, you just multiply the representative elements A and B together, and then apply that to the subgroup N. Okay, so I think right at the end last time we had gone over and looked at Cauchy's theorem for finite abelian groups, but we didn't get into the proof. So understanding the subgroups of a group is important to understanding the group. Lagrange's theorem gave us a necessary condition for a subgroup to exist, but it did not give us a sufficient condition for existence. Remember that Lagrange's theorem said that if you are a subgroup of the group, then your order must divide the order of the group. We did find out that there must be at least one subgroup of prime order that divides the group order, but we didn't find out which prime divisor it is. So Cauchy's theorem tells us that there must in fact be at least one subgroup of order P for each prime divisor of the group order. I will say, however, that this theorem only applies to finite abelian groups, so it's not for every group, but just for the finite abelian ones. So theorem 27.11, Cauchy's theorem for finite abelian groups. Let G be an abelian group of finite order n. If P is a prime divisor of n, then G contains an element of order P. And so, of course, that element of order P would generate a subgroup of order P as well. Okay, so let us go over the proof for this theorem. The proof is actually pretty challenging, so you're going to want to read it slowly, pause when you don't understand things to look them up. You might need to read it more than once. It's a kind of standard thing in math to need to read things more than once and incredibly slowly. I myself have a paper that I've been trying to read for more than 10 years, and I've never finished it. So, okay. Proving Cauchy's theorem. So before we get to the actual proof, we're going to do a little activity that's going to make it easy for us. So we'll see that the construction of a quotient group actually allows us to reduce the order of a group, and then we're going to be able to do induction because of that. And that's a pretty powerful idea, so we're going to explore it in this activity. So preview activity 27.12. So this is all just the instructions for the activity. The activity is actually on the next slide. So the instructions here, let G equal U21, which is the group of units in Z21 under the multiplication operation. So usually when we're in Z mod some number, we're usually doing addition, but for the units we can do multiplication for the operation. So this group consists of the following 12 elements. So these are all of the elements where they are relatively prime to 21. In case you forgot, that's what units are. They are relatively prime to the modulus 21, so that allows them to have a multiplicative inverse. So this group has order 12, so Cauchy's theorem tells us that G must contain elements of order 2 and 3. If we accept Cauchy's theorem, of course we haven't proved it yet, but that's what it would imply. So since U21 is a finite group of relatively small order, we could of course just determine the order of each of its elements, but our goal in this activity is going to be to create a general process that will allow us to find an element of whatever order we like in a finite abelian group. So we're going to try to do this in as sort of general a way as possible. So in this activity, we're going to try to find an element of order 3 in U21. So to find such an element, we will start with corollary 26.13. So that was the corollary of Lagrange's theorem, which tells us that G must contain an element of some prime order Q that divides the group order. Remember, however, that that corollary did not tell us what Q actually is, just that it has to divide the group order. So suppose that Q does not equal 3. Then by corollary 26.13, Q must equal 2, since 2 would be the only other prime that would divide 12. So what we're going to do is we'll pick an element of order 2 in G. So 8, for example, is an element of order 3, or sorry, of order 2. And then we're going to let n be the subgroup generated by that element, 8. So remember that the subgroup generated by an element, it's denoted like that with the angle brackets, and then that is just all of the integer powers of that element. And so in this case, it's actually only 1 and 8. For example, when you do 8 squared, you get 64, and then if you do 64 mod 21, that brings you back down to 1. So you only get 1 and 8 that are in that group. So since G is abelian, that automatically means that all the left and right cosets will be the same. So that means that n is a normal subgroup. So that'll always be the case in an abelian group, that all subgroups will be normal. And that means that this G mod n, which we're going to denote G bar, so that is G bar, it's got a little bar above it. We're going to call G bar G mod n. That will in fact be a group because n is a normal subgroup. Okay, so here is the actual preview activity, 27.12. So I just kind of summarized some of the instructions there that were on the last slide, and then it has the actual parts A, B, and C for you to do. So go ahead and pause the video and try this activity, and then we'll go over it. Okay, so let's go over the answers here. So part A, explain why the order of G bar is less than the order of G. This step will be important in the inductive proof of Cauchy's theorem. Okay, so I think the easiest way to explain is just to remind you that G bar is G mod n. And when you're doing the order of G mod n, so that is the number of cosets of n. And remember that the number of elements in the group divided by the number of elements in the coset, that will be the number of cosets. So you can actually just do it like this, it's pretty easy. So the number of elements in the group is going to be 12, and then the number of elements in n is 2. And so this is going to be 6, which is less than 12. Okay, so this is the pattern that we'll see in general. If you have a normal subgroup of more than one element, then when you want the order of the G mod n group, it's always going to be less than the order of the entire group because n has more than one element. So you'll always be dividing by some number that's greater than 1 there. Okay, so note that G bar equals n, 2 times n, 4 times n, 5 times n, 10 times n, and 13 times n. So those are the elements, the cosets that are in G bar. The operation table for G bar is given in the table. Show that 2n has order 3 in G bar. Okay, so how are we going to show this? So what I'm going to do is I'm just going to take the integer powers of 2n. So let's see, if we do 2n squared, that would be this, so 2n times 2n. And remember that the way we do this operation on cosets is we just do the operation on the two representative elements that are out in front, like this, and then multiply that times n. So what is 2 times 2? That is 4. Okay, and now let's take the next power. So if I do 2n cubed, I can write that as 2n times 2n squared, which I already know what that is. So this is going to be 2n times 4n. So that gives me 8n. But that is actually equal to n, and the reason is because 8 is an element of n. So that is n in n. So if the element that you're using as the representative is actually an element of n, then all you're really getting is n again. Okay, so that is part B. Okay, so let's look at part C. If G bar equals G mod n contains an element of order 3, it might be natural to expect that there is a corresponding element of order 3 in G. However, this is not always the case. For example, 2n has order 3 in G bar, we just showed that, but the order of 2 is not equal to 3 in G. So find the order of 2 in G, and then using only what you know about finite cyclic groups and the order of 2 in G, find an element of order 3 in G. This shows that G contains an element of order 3 as desired. Okay, so first let's find the order of 2 in G. All right, so let's think about what are the powers of 2. So the square power is going to be 4, and then if I cube 2, I'm going to get 8, and then if I raise 2 to the 4th, I'm going to get 16, and then if I raise 2 to the 5th, oops, then I'm going to get 32, but 32 is not actually an element of Z21. It's actually, or sorry, well, yeah, it's not an element of Z21. It's also not an element of U21. So when I get 32, I'm going to reduce that modulo 21. So this is actually going to be 11. Okay. And so let's keep going because I haven't gone all the way around and gotten all of them yet. So let's see, 2 to the 6. So 2 to the 6th would be 64. And if I reduce that modulo 21, that is actually going to be 1, the identity. So once you find the identity, you can stop because all the powers after that will just repeat through the ones that you've already gotten. So basically what we're seeing here is that the subgroup generated by 2 is the following. So it's 2 itself, that's the first power, and then it's 4, and then it's 8, and then 16, and then 11, and then 1. So the order here of 2, which is the same as the order of its subgroup that it generates, is, oh, too much notation in this line, is going to be 6. So what we do know about finite cyclic subgroups, or sorry, cyclic groups, is that they always contain a subgroup of every order of every prime that divides the group order. So let me just say that right here. So finite cyclic groups with order, let's call it M, have a subgroup for every prime P that divides N. Okay, so that means that the subgroup generated by 2 has a subgroup of order 3, which must be generated by some element, because these subgroups are also cyclic. Maybe I should put that in there. Have a cyclic subgroup. So that was one of the things we learned in a previous investigation. How did I just spell that? That's an L. Okay, cyclic subgroup for every prime P that divides N. So this subgroup generated by 2 has a subgroup of order 3, which in fact is generated by, what is it generated by? Let's see. I think it's generated by 4, because you'd have 4 and then you'd have 16, which is 4 squared, and then you'd have 4 cubed is 64, which would be 1 again. Okay, so we found an element of order 3. Okay, so now let's get into the actual proof of Cauchy's theorem, which I warned you was going to be kind of hard. So the previous activity demonstrates the method that we're going to use to prove that for any prime divisor P of the group order N, there is an element of order P. So basically, let me summarize what we're going to do. So first of all, we're going to find an element A in G of some prime order Q that divides N, and we won't be able to control what Q is, but we just know that there is some Q that has a subgroup of that order. So if Q is not equal to P, then the quotient group, I mean, obviously if Q is equal to P, then we're done. So if Q is not equal to P, then the quotient group G bar, which is going to be G mod the subgroup generated by A, will have a smaller order than the order of G. So if P divides the order of G bar, then we can apply induction and find an element B bar in G bar such that the order of B bar is equal to P. So it's going to go inductively. And then we can associate the element B bar in G bar with an element B in G such that B bar is equal to B times that group generated by A. And then if the order of B is a multiple of P, then we'll be able to find an element of order P in G. So that's basically the main idea, and let's go through that in detail. And like I said, this is challenging, so pause if you need to, look things up, listen to things more than once. Okay, let's do it. So let's read Cauchy's theorem for finite abelian groups one more time. Let G be an abelian group of finite order n. If P is a prime divisor of n, then G contains an element of order P. Okay, so proof. Throughout the proof, we're going to assume that G is an abelian group of finite order n with the identity element E, and we're going to let P be a prime divisor of n. So here's the statement that we're actually going to induct over right here. So let capital P of n be the statement, if P is a prime divisor of the order of G, which we're calling n, then G contains an element of order P. So we're going to proceed by strong induction, and since the smallest prime number is actually 2, we really don't need to look at the case where G is just one element. I mean, that's a really boring group that doesn't have any prime divisors at all, because there's no prime that divides 1. So we're going to start with the base case being where the group order is 2. So we'll show that capital P of 2 is true for the base case. Okay, so basis step. So we're down here now. So let the group order be 2. When the order of G is 2, the only prime that divides the order of G is 2. So we simply need to show that G contains an element of order 2. A group of order 2 can be written as the set EA, and if you're able to write your group like that, then the group generated by A is actually the entire group, because the group generated by A must at least contain the identity and the element A itself. So that will in fact be the whole group. So A is an element of order 2. Okay, so now let's do the inductive step. So we're going to assume that P, capital P of K, is true for all K less than n, and then we're going to show that P of n is true. So in other words, to expand on that, assume that for any abelian group G prime of order K which is less than n, and for any prime divisor Q of K, that G prime contains an element of order Q. So that is our inductive assumption. And now what we're going to show is we will show that for any finite abelian group of order n and any prime divisor P of n, that G contains an element of order P. Okay, so let G be a finite abelian group of order n, and let P be a prime divisor of n. By Corollary 26.13, so remember that was the corollary to Lagrange's theorem, we know that G contains an element A of some prime order Q. So if Q equals P, then we're actually done, because we've already found the element of order P. Well, that would be too easy, so we got to consider the other case where Q does not equal P. So we're going to assume now that Q does not equal P. Then let n be the subgroup generated by the element A. So n is going to be of order Q. So since G is abelian, that automatically means that n is a normal subgroup of G, because the left and the right cosets will be the same because it's abelian. So that means that G bar, which is what we're going to call G mod n, that will be a group. Then since A has prime order, we also know that the order of A, which is equal to the order of n, is going to be greater than 1. That's because all primes are greater than 1. So that means that the order of G bar, which is the order of G mod n, which is the same as the order of G divided by the order of n, that must be less than the order of G, because the order of n is greater than 1. Okay? So that means that the order of G bar is going to be less than n. And then furthermore, since G is abelian, so is G bar. So that will just be inherited from G. So that means that we can apply the inductive hypothesis to G bar. G bar is a finite abelian group, and it is of an order that is less than n. So we're going to apply the inductive hypothesis to it. Since P divides n, and P does not divide Q, of course P doesn't divide Q because those are two different primes, that means that P must divide G bar's order. Okay? So P does divide the order of G, but it doesn't divide Q. And remember that the order of G bar is given by this right here. It's the order of G divided by the order of n. The order of n is Q. So you've taken that n and you've divided out a Q, but you have not removed you have not removed the factor of P. Okay, so that must still be in there. So P is going to divide G bar. So by the inductive hypothesis, there must be an element B bar in G bar with the order of B bar equal to P. And remember, the inductive hypothesis is basically assuming that Cauchy's theorem is true for any group whose order is smaller than n, and the order of group G bar is smaller than n. So we're applying that. I hope this is still making sense to you guys. I feel like it's already kind of difficult even for me. Okay, so let's go to the next slide. Okay, so let's continue. So note that since B bar is an element of G bar, that means that there exists some B in G such that B bar is equal to B times n. Remember, all those elements in G bar, they are cosets, so it must be some coset. So that's all that's saying. Now recall that the order of B bar is equal to P, So that means that b times n, that coset, is not the identity in G bar. Because if it were the identity, that would mean that its order would be 1, but its order is not 1, it's p. Okay, and then furthermore, since b bar is equal to p, that means that if we raise bn to the p, we should get n. Because whenever you raise any element to its own order, you always get the identity. Then, since we also have that bn to the p equals bp to the n, it follows that bp to the n equals n. So where's that coming from? It's coming from these two equations right here. We have bn to the p equals n, and over here we have bn to the p equals b to the pn. So we have the same thing equaling two different things. That means those two other things are equal to each other. Okay, so since bp times b to the p times n is equal to n, that means that b to the p must be an element of n. That's because b to the p must be in this side, and so it must also be in this side. Okay, so b to the p is in the subgroup n. Now, note that b is, I think this is actually a typo, I don't think this is supposed to be here, that word. Note that b is not equal to the identity, since that would imply that bn is the identity in G bar. So if b were equal to the identity, then b times n would be n, and so bn would be the identity in G bar, but we already noted that bn is not the identity in G bar. Okay, so that means b cannot be e. So to summarize, what we've found so far is that b is a non-identity element in G, such that b to the p is an element of n. So now we're going to consider two different cases. Either b to the p is the identity or it is not the identity. So if b to the p is the identity, then since b is not the identity, b must have the order p, and we have found an element of order p in G, and we're done with the proof. You might want to pause and kind of think about for a little while why exactly b to the p equals e, and b not equaling e would mean that b has to have order p. So think about that for a little bit. Now, on the other hand, the other case is where b to the p does not equal the identity. So remember that the order of n, which is equal to the order of A, that was the group where we got n from, is also equal to q. And so the order of b to the p must then be q. So this is just because any element that is in a cyclic subgroup must have its order dividing the order of the cyclic subgroup. So the only possibilities for the order of b to the p, which is an element of n, the only possibilities are that its order is either 1 or q, because q is prime, so we can't break down q any further. Okay, so if the order of b to the p is q, that would imply that b to the pq, so this would be like b to the p to the q, like that. If you raise an element to its own order, you always get the identity. So we would get the identity from that. And so that would mean that the order of b must divide pq. So whenever you have an element and you raise it to some power and you get the identity, that means the order of that element must divide that power to what you raised it. So the possible orders of b are the following. The orders of b are either 1, p, q, or pq. So we already argued that it can't be 1 because we argued that b cannot be the identity. So the order of b cannot be 1. Of course, if the order of b is p, then we're done, because that's exactly what we're looking for. We're looking for an element of G that has the order p. So the only two cases that are left for us to look at are the cases where the order of b is q and where the order of b is pq. Okay, so let's consider those cases. So if the order of b is q, then that would mean that b bar to the q, which can be written like this, b times n to the q, which would also be b to the qn. That would imply that this b to the q, if the order of b is q, then it would be able to be reduced to e like that. Any element to its own order is e. And so that would, of course, give us n for that coset there. And so what that would mean is that you've raised b bar to the q and you've gotten the identity. So that would imply right there that the order of b bar must divide q. Okay, but we already said that the order of b bar is p, which is a distinct prime not equal to q. So that is actually impossible. Okay, so that case never happens. So now let's consider the last case. If the order of b is equal to pq, then Theorem 23.6 says the following. It says that the order of b to the q must equal pq over the GCD of pq comma q, and that would be p. So then if that is the case, then b to the q would actually be an element of G of order P. And that's exactly what we've been looking for. We don't really care which element it is, just some element of order P. Okay, so we have dispensed with all the cases, and we showed that in each of them, they're either impossible or G contains an element of order P. So that is the proof. I found myself getting a little confused as we were going over it, and I had to like pause and stop and think about things sometimes. So certainly you will need to do that as well when you're going over it. Stop and, line by line, try to understand why each line follows from the next, and the things that they're referencing that you might have forgotten about. Okay, so now let's talk about a corollary that we get right away from Cauchy's theorem. So one consequence of the theorem is that we can immediately determine the structure of all abelian groups of order PQ, where P and Q are distinct primes. So corollary 27.13 says, any abelian group of order PQ, where P and Q are distinct primes, is cyclic. This is kind of surprising, but let's see why. So proof. Let P and Q be distinct primes, and let G be an abelian group of order PQ. Cauchy's theorem for finite abelian groups tells us that G contains an element A of order P and an element B of order Q. So since the GCD of the orders of A and B is equal to 1, and G is abelian, it follows, and here they're saying to look at exercise 18 of investigation 23, that the order of A times B is PQ, and so that would mean that AB, the cyclic group generated by AB, would be that entire group. Since that cyclic group generated by AB, it would of course have to be a subgroup of G, and then if it's the size of G, then it must be G. So hence G is a cyclic group, and it is generated by AB. So that's quite interesting. So we've encountered some groups before that were of orders where it was two primes multiplied together, but we may not have realized at the time that they were actually cyclic groups. Okay, so one thing that mathematicians have been trying to do for centuries, actually, since algebra has been around, is we've been trying to classify all of the groups of finite order. And what I mean by classify is a little bit murky, but it basically means to find, to understand, to determine. We've been trying to do that for all of the groups of finite order. I mean, a group of finite order, it seems like you should be able to work out what they all are. Like, for example, there's, like Z2, Z3, Z4, those ones. There's the symmetric groups, there's the alternating groups, there's the dihedral groups. But unfortunately, we have not yet been able to work out what all of the groups of finite order are. We have, however, over many centuries of continuous collaborative work running into the thousands of pages of journal articles, we have been able to classify all of the finite simple groups. So let me tell you what a simple group is. A group G is simple if G has no non-trivial proper normal subgroups. So just to note here, a proper subgroup is one that is not the entire group, and a non-trivial subgroup is one that is not just the identity. So this is saying that a group is simple if it has no normal subgroups other than the entire group and the identity subgroup. Those you always have, of course. Okay, so let's look a little more at this. So let's talk about the simplicity of the alternating groups. So the alternating groups, AN, these are actually an important example of simple groups because these are used to show that there is no possible formula for finding the roots of a polynomial of degree 5 or higher with real or complex coefficients. And the fact that there is no formula for finding those roots for polynomials of degree 5 and higher, that is one of the most celebrated and the most important results in all of mathematics. I hope that you actually knew about that from some other class, but if you didn't, you remember that there's the quadratic formula for finding the roots of a polynomial. It's this one, x equals negative b plus or minus square root of b squared minus 4ac all over 2a. So that's a quadratic formula. That's for finding the roots of a quadratic polynomial. And then there is actually a cubic formula, and there is even a quartic formula that are very similar to that formula, except much, much longer. I think the quartic formula fills up like a whole page. That you can use to find the roots of a polynomial of degree 3 or 4, but there is no formula for degree 5 or higher, and it took us actually like thousands of years to be able to prove that from the first time that people sort of started wanting to solve equations. Okay, so let's talk about the simplicity of these alternating groups, and we're not actually, unfortunately, going to be able to work up to proving that thing about the polynomials, because you would have to work your way all the way through rings and then into fields and then field extensions. But we can still talk about this alternating group being simple at least. So remember that the alternating group AN is the set of even permutations in Sn. Remember, Sn is the symmetric group. So that is the permutations of 1, 2, ... up through n. And the ones in the alternating group are the ones that can be written as the product of an even number of transpositions. So this is the important part. Even number of transpositions. And just to remind you, if you forgot what a transposition is, that is a cycle of length 2. It just switches two numbers. So the next activity is going to demonstrate the general idea of how we will show that AN is simple. Okay, so here's the activity. So go ahead and pause the video, try this activity, and then we'll go over it. Okay, so let's go ahead and go over this. Let n greater than or equal to 3 be an integer, and let a, b, and c be elements of the set 1, 2, 3, ... up through n. So part A, write the product AB, AC as a cycle or as a product of disjoint cycles. And why does this show that AN contains every 3 cycle? Okay, so this is not too hard, I think. So let's try doing it as a cycle. So AB, AC. All right, so let me think about where A gets moved to by this. So first A gets moved to C, and then this other element here, that does not move C anywhere. So A is going to go to C. All right, now let me think about where C gets moved to. So first C goes to A, and then A goes to B. So in all, C goes to B. Okay, and now let me think and just make sure that B actually does go back to A, although I'm pretty sure it does. Okay, so B, it doesn't go anywhere in that one, and then in this one it goes to A. Okay, so good. This is my whole cycle right here. All right, so this is a 3 cycle. So why does this show that AN contains every 3 cycle? So what I can say is that every element of the form AB, AC is going to be in the alternating group because this is an even product of transpositions. Even product of transpositions. And then every 3 cycle can be written in this form. Yeah, so they're all going to be in AN. Okay, part B, write each of the following products as a product of 2 transpositions. Okay, so let's see if we can do this, whether it's actually possible or not. So let me see, where is 1 going to be moved to? So where is 1 going to move to? Let's see. So first 1 is going to go to 3, and then 3 is going to go to 2. So 1 is going to go to 2. All right, now let me see where 2 goes to. 2 goes nowhere in there, and then in this one, 2 goes back to 1. Okay, so that is the first transposition right there. It moves 1 to 2 and 2 to 1. Okay, let's see where 3 goes to. So 3 is going to go, first 3 is going to go to 4, and then 4 goes nowhere in there. So this is going to be 3 to 4. And then let's just check and make sure that 4 goes back to 3. So let's see, 4 is going to go to 3, and then 3 is going to go to 2. Oops, I did that wrong, didn't I? Okay, so 4 is going to go back to 1, and then 1 is going to go to 3. So 4 does go to 3. Okay, so those are my 2 transpositions. I figured out where all 4 elements went to. All right, let's look at the next one. I don't know if you remember this, but you can write any cycle like this by just kind of breaking up, like you just do the first 2 elements and then the second 2 elements like that. So that one can be written like that. And then let's do this last one. Okay, so where does 1 get moved to? So 1 goes to 3, and then 3 goes back to 1. Okay, so 1 doesn't go anywhere. All right, let's see where 2 goes to. So 2 goes to 1, and then 1 goes to 2. Oh, so 2 doesn't go anywhere. Okay, let's see about 3 and 4. Well, just 3, actually. Let's see, where does 3 go? So 3 goes to 2, and then 2 goes to 3. Oh, 3 doesn't go anywhere either. So, okay, this is actually just the identity. None of those elements get moved anywhere. Okay, so we did it. Actually, did we quite do it? Because they asked us to write this as a product of 2 transpositions. So I guess if I was really forced to write this as a product of 2 transpositions, I could just do 1 transposition that is its own inverse, like that. So that's basically just the identity again. Okay. Okay, so now let's look at a lemma that kind of follows along from the last activity that we just did. And remember that a lemma is a theorem that you prove usually to help you prove a bigger theorem. So in this case, the bigger theorem that we're interested in is showing that an is actually simple. So this is going to help us do that. So the lemma is 27.16. Let n be an integer with n greater than or equal to 3. Any permutation in an can be written as a product of 3 cycles. Okay, so here is our proof. So let n be an integer with n greater than or equal to 3. Note that each 3 cycle ABC, which can be written as ACAB, is an even permutation. So 3 cycles are already even permutations. So an must contain all of the 3 cycles. It's the same as what we just argued on the last activity, because they can all be written in the form of an even number of transpositions. Okay, so now let sigma be an element of an. Then there exist transpositions tau 1, tau 2, up through tau m, such that sigma equals tau m, tau 3, tau 2, tau 1. Okay, so this is just the characteristic of being in the alternating group, is that you can be written, well, actually any permutation can be written as a product of transpositions. And then since sigma is an element of the alternating group, that means that the number of transpositions is even. Okay, so if m is even, then that means there's an integer k such that m equals 2k. Okay, so then what we can do is we can collect these little taus into groups of 2. So here's how we're going to collect them. So we're starting with 2k and 2k minus 1. That's the same as m and m minus 1. So that's our first little set of 2 transpositions, and then we just keep going along like that until we get to the end, which is tau 3 and tau 2, or sorry, tau 4 and tau 3, and then tau 2 and tau 1. Okay, so let's talk about this a little more. If in any pair we have that tau 2i equals tau 2i minus 1, then tau 2i minus 1 would be the identity, since the same transposition is its own inverse, and it can be removed from this product. So if we have any that are like that, then we can just delete them, and we'll still have a list of pairs of transpositions like this. So therefore, we can assume that none of these are the same, because if they are the same, we'll just delete them. So we can assume that none of them are equal. Okay, so it follows that each pair has the form like this, transposition of AB and then the transposition of CD, with A not equal to B, C not equal to D, and AB not equal to CD. Let's break those down. So the reason why A is not equal to B is because if A was equal to B, it wouldn't be a transposition. It would just be the identity. And that's the same reason why C is not equal to D. If they were equal, it wouldn't be a transposition. It would just be the identity. And then the last one here, AB not equal to CD, that's what we just argued about in the previous paragraph. Okay, so there are 2 cases that we must consider. Okay, so this is what we just had on the last slide. So there's 2 cases that we must consider. So the first case is when A, B, C, and D are all distinct. So in this situation, we can actually rewrite A, B, C, D. We can rewrite it as 3 cycles like that. You guys can just check on your own whether those actually work out to be the same thing, but they do. Okay, so the other case is when A, B, C, and D are not all distinct. So if they're not all distinct, then one of A or B must equal one of C or D, and it sort of doesn't matter which one you think it is, because we already don't know what these A, B, C, and D actually are. So we're just going to pick one letter from each transposition and say that they're equal. So that's what they're explaining in this paragraph here. So they're saying the other case is when B equals C, so they're just picking B and C to be the ones that are the same, and A is not equal to D. Of course, if A was equal to D, then we would have that AB equaled CD, which we already said we can't have. Okay, so here they're explaining in parentheses why they're allowed to just choose B and C to be the same ones. So this case is equivalent to those in which A equals D and B does not equal C, or A equals C and B does not equal D. So those are the other ways that we could have chosen one element from the first transposition and another element from the second transposition to actually be the same. And it really doesn't matter which of those you pick, because as I said, we already don't know what A, B, C, and D are. So if you picked the wrong one, then you can just rename all of the numbers that were actually in there by the letters that make B and C be the same and A and D be different. So therefore, we will assume without loss of generality that B equals C and A does not equal D. And remember, I think we talked about this previously in the class, but the phrase without loss of generality means that you're saying something that while it might not be true technically in general, it is true if you rename all of your variables. So you can rename your variables in such a way that nothing changes and what you've said is true is actually true. Sorry, I don't know how good of an explanation this actually is when I'm just kind of talking to myself in my room, but I am trying. Okay, so then if that's the case, then ABCD is equal to ABBD, so we just replace C with B, and that is going to be equal to this 3-cycle ABD. Okay, so what we see in each case is that we can always write a product of 2 transpositions in terms of 3 cycles. Okay, so we either have it like this, or we have it like this. Okay, so every even permutation, that is every element of AN, can be written as a product of 3 cycles. And that is the proof. Okay, so now let's talk about some consequences of that lemma that we just saw. So the fact that AN is generated by the 3 cycles also tells us something about the normal subgroups of AN, and that's what we're trying to work up to. We're trying to show that there are no normal subgroups of AN except for AN itself and the identity subgroup. So let's do this activity here. Go ahead and pause the video and try this activity, and then we'll go over it. Okay, so let's go over the answers to the activity. So let n be greater than or equal to 3, and suppose n is a normal subgroup of AN that contains the 3-cycle 1, 2, 3. So why must n contain the 3-cycle 1, 3, 2? So I hope you've actually worked with S3, the symmetric group on 3 elements, enough at this point to know that 1, 2, 3 squared is actually 1, 3, 2. So that's the answer, because if 1, 2, 3 is in the subgroup, then of course all of its integer powers must also be in the subgroup. So that's that. All right, part B, let R, S, and T be elements of 1, 2, 3, dot, 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 up through n. Write each of the following products in AN as a cycle or a product of disjoint cycles. Why must each of these elements be in? All right, so let's look at this. So I'm just going to try my usual technique here for figuring out where all the elements go. So I'll just start with 1. So first 1 goes to 3, and then 3 goes to 1. Okay, so it didn't go anywhere. And then in this last one, 1 goes to T. So 1 is going to go to T. All right, let's figure out where T goes. So first T goes to 1, and then 1 goes to 2, and then 2 does not go anywhere. So this is going to be 2 here. All right, and let's figure out where 2 goes. So let's see, the only one that moves 2 is this one, and it moves it to 3. So that's going to be 3. Oh, I'm sorry, that was a mistake there, guys. So 2 goes to 3, and then 3 goes to 1. So 2 is going back to 1. Okay, so that is that cycle right there. And then where does 3 actually go to? So where is 3 going to go to? Let's see. So 3 goes to T, and then T is going to go back to 3. So 3 doesn't actually go anywhere. And okay, so I think that covered all 4 of those elements that were in there. All right, let's try part 2. So where is 1 going to move to? So first 1 goes to R, and then R doesn't go anywhere there, and then R goes back to 1. So 1 in fact goes nowhere. Okay, let's try 2. Where does 2 go? Okay, so 2 goes nowhere in there, and then 2 goes back to 1 here, and then 1 goes to T here, so 2 goes to T. Okay, where does T go to? So first T goes to 1, and then 1 goes to T, and then T goes to R, so T is going to R. All right, and then where is R going to? First R goes to T, and then T goes to 2, and then 2 goes nowhere, so R goes to 2, so that's that whole cycle there. And that was all 4 of those elements. All right, let's try the last one. So where does 1 go? First 1 goes to S, and then S goes back to 1, so 1 goes nowhere. All right, where does 2 go? So first 2 goes to 1, and then 1 goes to 2. Okay, so 2 doesn't go anywhere either. All right, and then where does R go? So let's see. So R goes nowhere, and then it goes to 2, and then 2 goes to S. So R goes to S. Okay, and where does S go? So first S goes to 2, and then 2 goes to T, and then T goes nowhere. So S goes to T. Okay, and then where does T go? So let's see, nowhere, and then T goes to R, and then R goes nowhere. Okay, so this is just RST. Okay, so explaining why these actually have to be in N is a little bit trickier to do. So recall that for a normal subgroup N, that means that AN must equal NA. So that would imply that AN A inverse equals N for all elements A in the group. Okay, maybe I should say it like this, that when N is a normal subgroup of G, like that. Okay, so that means that because 1, 2, 3, so coming down here, so because 1, 2, 3 is in the subgroup, and 1, 3t is in the group, or maybe I should say AN, and 1t3 is actually the inverse of 1, 3t. Okay, so what you're doing there is you're actually multiplying A times something in the group times A inverse, so you must be getting something else that is in the group. So that's a little bit confusing, but that's where that is coming from. So 1t2 must be in N. Okay, and it's the same for the rest of these. Basically, once you found something that's in the group N or the subgroup N, like this is now N, this is in N, and then these two are inverses of each other. Then whatever result you get, it has to be something that is in N, that subgroup N. So those are inverses. Okay, so that is why all those elements must be in N. And then part C, how does the result of part B show that N equals AN? So look at the very last thing that we got in part B. So the last thing we got in part B is that RST is in N, and then RST, those are just some random elements of, they could have been anything out of 1, 2, 3, ... N. So because of that, we've actually shown that anything that is a 3-cycle can be written in the form RST, so all of those will be in N. And so we showed before that all of AN can be written as products of 3 cycles. So yeah, we've done it. Let me see if I can just summarize that last part. Can be written as products of 3 cycles. Right, so N is containing all of the 3 cycles, and then all of AN are products of 3 cycles. Yeah, so all of AN is products of elements that are in capital N, and that means that all of AN is in capital N. Yep, so that's it. Okay, so from there, we're going to do another lemma where the proof is actually going to just mimic exactly what we did on the last activity, and if that last activity didn't quite make sense to you, then I hope it will after reading this lemma's proof. So activity 27.17 seems to provide a method for generating all 3 cycles in a normal subgroup of AN that contains a 3 cycle. So this is the lemma that will show this in general. Lemma 27.18, let n be an integer with n greater than or equal to 3. If capital N is a normal subgroup of AN and capital N contains a 3 cycle, then capital N must be equal to AN. Okay, so let little n be an integer with little n greater than or equal to 3, and let big N be a normal subgroup of AN, and let ABC be a 3 cycle that is in big N. We will show that big N equals AN by showing that n contains all possible 3 cycles. Then lemma 27.16, which was the last one, will establish that n equals AN. So let RST be integers between 1 and n. Since big N is normal in AN, we know that alpha times ABC times alpha inverse is in big N for every alpha in AN. So from lemma 27.16, we also know that AN contains all 3 cycles. Therefore, we can do the following. So we can write ATC, ABC, ACT. So these two are inverses of each other. These are inverses. And then ABC is the one that is in, so that one right there is in capital N. Okay, so if you multiply the inverses, alpha and alpha inverse on either side of something that is in capital N, then you'll get a result that is also in capital N. So that means the result that you get here, which is ATB, that is going to be in capital N. Okay, and so then once you have that, you can move that ATB to be the middle element, and then you can again apply an element and its inverse on either side like that, and you'll get another thing that must be in capital N. Okay, and then you can do it again. You can move that last element that you just got to be in the middle there. So you have a center is an element in capital N, and then on either side are two elements that are each other's inverse from AN. Okay, and then if you multiply all that together, you get RST, and that must be an element of N. Okay, so since R, S, and T were chosen to be arbitrary integers between 1 and n, that shows that capital N contains every possible 3-cycle. And since we know that everything in AN can be written as products of 3 cycles, that means that n is going to be equal to AN. Okay, so finally we've worked our way up to being able to prove the theorem that we've been building up to with these lemmas. So this is theorem 27.19. Let n be an integer with n greater than or equal to 5, then AN contains no non-trivial proper normal subgroups. Okay, so here's our proof. Let n be an integer with n greater than or equal to 5, and suppose that n is a non-trivial proper normal subgroup of AN. So we're going to show that this leads to a contradiction. So let sigma be a non-identity element in n that permutes the fewest number k of integers. So if k equals 3, then sigma must be a 3-cycle, and then lemma 27.18 would show that capital N would equal AN, which is a contradiction because we assumed that big N was proper. So if n is equal to the whole group, then it would not be proper. Okay, so that's a contradiction. So then we have to assume that k is greater than or equal to 4, and then we're going to decompose sigma into a product of disjoint cycles. So we're going to rewrite sigma as sigma 1 times sigma 2, sigma 3, etc. up through sigma m, where all of these are disjoint cycles. So we know we can always write any permutation as a product of disjoint cycles like this. You might be wondering at this point, like, why didn't we consider the case where k equals 1 or 2? Remember, k is supposed to be the fewest number of integers that are permuted by any element in AN. And so if that element of AN permuted only 2 integers, then it would be a transposition. So it would be one transposition, but there's no single transposition that's in AN because AN contains products of an even number of transpositions, okay? So that's not actually possible. And then if it only permutes one number, well, that's just not possible to begin with. You can't have a permutation that only permutes one number because wherever it goes, something has to come in and fill its place. Okay, so that's why these are our cases here. We showed that k equals 3 is a contradiction, so we're looking at k is greater than or equal to 4, and we don't have to consider anything lower. Okay, so we have decomposed our element sigma that permutes k elements into a product of disjoint cycles, which are here. And now we're going to consider two cases. So for some I, sigma I is a q cycle with q greater than or equal to 3. And if that is not the case, if there is no sigma I like that, then for each I, sigma I is a transposition. So that would be the case. If case 1 is false, then case 2 would be the case. Okay, so let's consider these two separately. Okay, so in case 1, we're saying that for some I, sigma I is a q cycle where q is greater than or equal to 3. So in this case, we can assume without loss of generality that we can write sigma in the following manner. So it's the cycle 1, 2, 3, dot, dot, dot. We don't really know where it ends at. It just starts with 1, 2, 3. And then tau, where tau is disjoint from the 1, 2, 3, dot, dot, dot part. So basically what we're doing by saying that sigma equals this is we're saying this is going to be the sigma I that we were talking about before. So that is the cycle that has a length of 3 or greater. And then we're just smushing the rest of sigma into that tau part. And why are we allowed to say that the elements that are in the cycle are actually 1, 2, 3? Well, it doesn't really matter what they are. We don't know what they are, so we might as well call them 1, 2, 3. it doesn't really matter what you call the elements that you're permuting. Just calling them 1, 2, 3 is going to make it easier for us to keep track of them. They could be something completely different, but the rest of this proof would still work the same, just swapping out 1 for whatever it actually was and 2 for whatever it actually was. So that's what's going on here. And then of course we know that we can always write any element as a product of disjoint cycles, so we can pull out that sigma I cycle to the front and then write the rest of them as one element, which we're calling tau. That'll be disjoint. Okay, so if sigma permutes exactly 4 integers, remember we said it permutes at least 4. If it permutes exactly 4, then sigma would have to be the following. It would have to be 1, 2, 3 a for some integer a which is not 1, 2, or 3. And then sigma would actually be odd. So if it permutes exactly 4 integers, you can see from the way we've written sigma with that 1, 2, 3 ... every element in the 1, 2, 3 ... will be permuted. So if it's permuting exactly 4 of them, then it must stop with the a there. It wouldn't be possible for it to be just 1, 2, 3 and then something else, since that other something else would have to permute at least 2 things. Oh boy, I don't know if this explanation is going good, but I am trying. Okay, so sigma would have to be 1, 2, 3 a for some integer a that is not 1, 2, or 3. And then what that would mean is a cycle of exactly 4 elements is actually an odd number of transpositions. That would actually be 3 transpositions multiplied together. It would be 1, 2, 2, 3, and then 3a. So that would actually be odd. And there are no odd elements. There are no products of odd numbers of transpositions in the alternating group, okay? So sigma would not be in, okay? So what that means is we've just showed that it is not possible for sigma to permute exactly 4 integers. So it must permute at least 5 integers. So we're up to here. So without loss of generality, we are going to assume that the image of 4 under sigma, so sigma of 4, is going to be called A4, and then sigma of 5, we're just going to call that A5. So we don't know what those are, but we're just calling them that. And now we're defining a thing called beta. So let beta equal 3, 4, 5. And now we're defining gamma. So let gamma equal sigma inverse beta, sigma beta inverse. So it's a bit mysterious where these came from. They're just being defined. So we'll find out why they're useful in just a moment here. So since n is normal in an, that means that if we take any element that's in n, like sigma, and then we do beta and beta inverse on either side of it like that, that must also be in n. So that was one of the things that we found out about normal groups. And so that is actually going to tell us that gamma must be an element of n. Why? Because gamma is sigma inverse times this beta sigma beta inverse, and sigma inverse is in n, and beta sigma beta inverse is also in n. So if you multiply 2 things together that are in n, then their product must be in n. Okay, so gamma is in n. Okay, and now what we're going to see is that gamma of 1 is going to be the following. So it's going to be all of that, and we're just going to apply one thing at a time here. So first we apply the beta inverse part to 1. So if we do beta inverse to 1, beta actually doesn't move 1 at all, so that's not going to do anything. So we'll still just have 1 here. And now we're going to do sigma of 1. So where does sigma move 1 to? So remember we said that sigma is equal to 1, 2, 3, ... a long cycle like that, and then tau, where tau is disjoint from the 1, 2, 3 part. Okay, so that means the only part of sigma that is moving 1 is that 1, 2, 3 ... part. Okay, so that's why the image of sigma of 1 is actually 2. And now we're going to do beta to 2. So beta does not move 2 at all, so this is still going to be 2. And then finally we're going to do sigma inverse to 2. So sigma inverse is going to do the opposite of what sigma did, so that is going to move it back to 1. Okay, so what can we tell from this? This actually tells us that because gamma of 1 was equal to 1, that means that gamma is not the same as sigma, because sigma of 1 is not 1. Sigma of 1 is 2. Okay, so gamma and sigma cannot be the same element. And so in addition, let's look at one more thing here. So what is gamma of 2? So if we do gamma of 2, just write out what gamma is there. Beta inverse of 2, that's not going to move 2 at all, because beta doesn't move 2. And then if we do sigma of 2, remember sigma starts with that cycle, 1, 2, 3, ... So that's going to move to 3, 2 goes to 3. And then we do beta to 3, that's going to go to 4. Okay, and then finally we do sigma inverse of 4. So We don't know exactly what sigma inverse of 4 is because we don't know whether that first cycle part of sigma goes on beyond 3. It's 1, 2, 3, dot, dot, dot. We don't really know whether that includes 4 or not. If it does include 4, then 4 either gets mapped to 1, or if it's even longer than that, if it's 1, 2, 3, 4, 5, then it would get mapped to 5. Or on the other hand, 4 might be mapped by something that's in tau. So if the beginning part of sigma is just 1, 2, 3, and then tau, then 4 might be moved by tau. But it would not be possible for it to be moved to 2, because the 2 is still part of that first cycle of sigma, and that means that the only thing that can be mapped to 2 is 1. I hope that's making sense to you guys. I feel like there's just words coming out of my mouth. I don't know if they make sense or not. They make sense to me. Okay, so 4 cannot be mapped to 2 by sigma inverse anyway. So what that means is that because gamma of 2 is not equal to 2, that means that gamma is not the identity permutation. Okay, so we found out that gamma of 1 is 1 and gamma of 2 is not 2. So gamma is not sigma, and gamma is also not the identity permutation. Okay, then another thing I want you to think about is that if t is greater than or equal to 5, and sigma of t is equal to t, then gamma of t will be equal to t as well. So why is that? That's because gamma is defined as sigma inverse beta sigma beta inverse. So t, by saying that t is greater than or equal to 5, or just greater than 5, that means that beta does not move t. And if sigma doesn't move t as well, then neither beta nor sigma moves t. Then gamma is composed of sigma inverse beta sigma beta inverse, so gamma would also not move t. Okay, so that would mean that gamma of t would equal t as well. Okay, but now look at what we've got here. So since gamma of 1 equals 1, this means that gamma permutes fewer elements than sigma, which is a contradiction to our assumption that sigma is the element of n that permutes the fewest number of integers. Okay, so this is quite interesting. So gamma, it doesn't move anything that's greater than 5, and it also doesn't move 1. So by not moving 1, it is actually moving fewer things than sigma. So this is a contradiction. Okay, so we just found out that case 1 never happens. So that means that we always have case 2. So case 2 is for each I, sigma I is a transposition. And in case you forgot what these sigma i's are, remember that we defined sigma is the element in n that moves the fewest number of elements. And we said that sigma could be written as a product of cycles like this. And so what we've just found out is that those must all be transpositions. Okay, so in this case, we can assume without loss of generality that sigma is equal to 1, 2, 3, 4, dot, dot, dot. So in this case, we're saying this without loss of generality, and we seem to be saying something pretty specific, but the fact of the matter is that if it is not true that sigma actually equals 1, 2, 3, 4, then we can just rename all of those elements from 1 to n until it does equal this. I know it's a bit of a dumb argument, but it really doesn't matter what you are permuting, whether you're calling them 1, 2, 3, 4, or A, B, C, D, or, you know, alpha, beta, gamma. So we're just going to say that sigma equals 1, 2, and then 3, 4, and so on and so forth. So we again let beta equal 3, 4, 5, and let gamma equal sigma inverse beta, sigma beta inverse. So then for the same reasons as before, well, actually not for quite the same reasons as before, but in this case, gamma of 1 is going to equal 1, and that is because neither beta nor beta inverse is going to move 1 at all, and then 1 is going to be moved to 2, and 2 is going to be moved back to 1 by the sigma and sigma inverse parts of gamma. Okay, so gamma of 1 is going to be 1, and then for the exact same reasons, gamma of 2 is going to equal 2. And then if sigma of t equals t for any t greater than 5, then gamma of t is also going to equal t. And that's because beta would not be moving that value of t because it's not one of the things that beta moves. And then if sigma also does not move t, then nothing in gamma, neither sigma nor beta, is going to move it. So gamma will also not move t. Okay, and also gamma of 3. So we can evaluate what gamma of 3 is by just plugging it into these different functions here, and we can find that gamma of 3 is not going to be equal to 3, so gamma is not the identity. But once again, we find that gamma, it permutes fewer elements than sigma, because it doesn't permute 1 or 2, but sigma does permute them. Okay, so this is actually a contradiction. So since both cases lead to a contradiction, we can conclude that AN contains no non-trivial proper normal subgroup. That is a typo. When n is greater than or equal to 5. Okay, so we had a lot of proofs today, guys, but we got through them and we finished investigation 27. If you got confused during any of those proofs, I know I did. You'll want to go to the book and read those in more detail and look up the things that you didn't understand and kind of pause and ponder and think them over and convince yourself that they are true. Please send me any questions that you have. If you need any help with the homework, with the test, let me know, and I'll see you guys next time.